Okay, welcome to the lab that is related to some of the things that we've talked about in Chapter 7. And part of this is going to be a little bit of a review, but what I'm hoping to do is show you some examples of using some of these different estimation techniques for estimating prediction error. And as usual, I have my kind of header up here. The package we're going to be using is the ISLR dataset package, which has a lot of data sets. And there's a couple of different Bootstrap packages which you can install from CRAN, and also the Leaps package, which has the subset selection stuff in there that we did before. And so what we're going to do is we're going to start out by we don't need to change the directory in this case because we're not actually going to save anything. But first thing we can do is load the data. Okay. And this data is data that you'll have to look at in your homework, I believe. Let me run this, okay? And if I do head auto, I can see this is some data set related to the automobile stuff, and I believe in your homework you kind of look at discretizing this MPG into 2 levels or something like that. But if we do help auto, we can kind of see all of the information here. So there's a lot of different types of variables here. We're typically interested in predicting this miles per gallon as a function of all of these different things that kind of have to do with the specifics on the car and how it functions. So I'm just gonna, sometimes I do this because I don't want to write over anything, but I'm gonna make this auto with a lowercase a. I'm just used to writing lowercase. So the first thing we want to do is we want to consider a very simple case, okay? Let's see here. And for this case, we might just consider the holdout method, okay? And now we've done this quite a few times already, but now I think we can just formalize it if we want to. And we can do this for a linear model. So if I can call train is equal to, the first thing I want to do is I want to set the seed. And the reason I want to set the seed is because, and I just set it as 1, it doesn't matter, it's because I actually use the sample command, which uses a random number generator to randomly select as many numbers as you tell it to in this interval, okay? And I'm going to tell it to select 80% of the number of rows of auto. So it tells that the dimension in this case is taking 80%. Oops. I better run it from here. Okay, so I think we're okay. And so we say train. We can see that these are the indices that it selects at random. And just to get an idea, this data set is 392 samples. Let's see. 392 by 9. Okay, so I'm just going to write that up here. 392 by 9. Okay. And the response variable is going to be this miles per gallon. And I'm going to create a variable called yTrain, which is going to be auto, MPG, the indices, which I've just sampled for training. Now I don't have to use a comma or anything because this is a vector. Auto MPG is just one column in the data set. So we call it accordingly. And the test data, as we know, is just going to be everything that is not in the train. So that's kind of easy to do. The X train, and I go a little bit fast here because we've been doing this a little bit. But we're going to use, in this case, let's do names, auto. Okay, so we're just going to actually use two variables to make it simple. 2, 3, 4, and 5. We're going to look at horsepower and weight as being the predictors. So train, we'll do 4 to 5. I can put this at a C if I want to. I don't need to. I'll just leave it like that. That's fine. And likewise, the test is going to be the same columns, but everything that is not in the training. Okay? And so if we want to fit a linear model, we could do so by just doing MPG, twiddle, horsepower, plus weight, because those are the variable names, and I can tell it the data is the auto data, okay, and it's the training part of the data. Okay, so that's one way I can do it. Notice I didn't use X yet or anything like that, but we can go down a little bit further. So let's run this data set. Oops, let's see. I can see that I can't spell correctly. Horsepower. Okay. So we run this and we can do summary fit. It's only two predictors. Okay. They're both significant. Okay, so far so good. Now let's look at test error. And this time I'm going to look at, well, actually, in order to do that, the first thing I have to do is I have to run a prediction, right? So I want to use pred.test. And for this, I'm going to do predict. Using the fit that I just got, I'm going to give it a new data set. And so now I have to do predict.lm so I can remember what the syntax is. And they want new data. So I'll tell it what the new data is. And it's x.test. Okay. So let us see what this looks like. And likewise, we have pred train. And I can give it the new data x train. And so this is going to give me responses of the training and the test. Now, you could actually grab the responses for the training right from the fit if you look at the fitted values. But anyways, I can do this as well. Now, we can compute the test error, which we would look at pred.test minus y.test quantity squared. So this is the residual sum of squares. And if we want the mean squared error, we can look at summing this up and divide it by 1 divided by, to keep it in the most general sense. Now I know that it's 392, actually it's 80% of 392, so I could figure out the dimensions of the training set. But to make it in the most generic way possible, I can just look at it like this. Okay. Now, this should be good. And now we will run this. Okay. So far so good. So test error. Uh-oh, that's not good. Let us run this. And let's look at pred.test and pred.train. So far so good. And test.error does not look good. So, oh, that's why. Length of y test is 0. So what happened here exactly? I'm going to run it from the beginning here. And let's look at y test. And it's null. Okay, the reason here is that, so I have a lot of practice debugging because I make all kinds of mistakes, and so you get to witness this a little bit live. But I have this misspelled. So now let's see if it works. Test.error is 19. Okay, so that's good. And now we can actually do the same thing for the training. And so I'm just going to copy and paste it. And we just can change this to train. And we can change this to train. Pred.train. And y.train. There. Perfect. Okay. And so down here, I'm just going to put test error and train error, just so it outputs it as we run through the loop. Okay. Not the loop, but as you run through the code, it's nice that you don't have to type it in here. Okay, so the training error is a little bit less than the testing error. And, okay. The next thing we're going to do is we're going to take a look at using this holdout method over a spectrum of complexity parameters. And those complexity parameters will come in the form of number of predictors and subset selection. So here we will utilize the holdout method over a spectrum of complexity parameters. We will also look at, since we're here, we'll look at the in-sample methods too. So we're going to use the subset selection techniques, and what we're going to do is we're going to cheat for a minute, and I just want to copy and paste this down here again because it's the same start. And once we have that, I'm going to actually do a trick where we put, okay, we're going to have y because we need y. We don't really need x, okay, because we're going to actually use the formula notation. And the way this works is a little bit different than the linear model. So we'll say training, in this case, is going to be the auto data set. And we need to make it a little bit more interesting, so we have to consider some more variables. So let's do head auto. And so we see 1, 2, 3, 4, 5, 6, 7. And so let's just look actually here at hist year bins is equal to 10. Oops. Auto. Okay, so we actually do have kind of a spread of that, so that's a pretty good variable. And, oops, I didn't really like that. I guess I'm outdated here. It's breaks, not bins. Okay. But the other variables are a little bit concerning. So, origin, that, let's just take a look at what that looks like. Okay, there's only three unique origins. They're encoded here 1, 2, and 3. And if we looked at the data set, we'll see the different kinds of origins. And we also see this one, which says there's 304 levels in this factor. These two are factors, origin and the name. And there's only 370 things, so there's almost no repetition here. These are pretty much unique identifiers, if you think about it. So we don't want to include that either. So we're going to end up including 1, 2, 3, 4, 5, 6, 7. 7 different variables. 1, 2, 7. And the same thing for test. We'll use the auto data set with everything that is not in the training set, and 1 to 7. So you should always look at these variables as a first step, and see that it would be pretty obvious that it would be best to leave that piece out, at least for this exercise. Now, the fit, we're going to use reg subsets. And MPG is our variable of interest, and I'm going to use all the predictors in the training set. And the method I want to use is the exhaustive subset selection, which incidentally I think it's the first one, so we don't really have to write this, but for completeness, I want to just stick it in there. And the number of maximum subsets I want to consider are 6. So everything except for the all possible subsets, all possible things. We have 7 variables here, but don't forget one of them is the predictor, and one of them is the response, rather. So this is good. So let's fit this model. Okay. And I can see that that was a mistake. Okay. The other thing we can do is look at names fit, and we can see that this one outputs the okay, it's not here. I forget, this is the weird one. It's summary fit. Okay. So what I'm going to do to make life easier is put my summary. It's going to be summary fit, because actually if you look at names, the in-sample information is here. Okay, oops. This should be like this. Let's try this one more time. Okay, so here we have what we want. We want, in this case, CP might be good. So let's put my summary CP, my summary BIC, and this is going to give me a range, okay, of values. And in fact, what I might want to do is plot them to take a look. And we might see that in this case, I can see that the winner is going to be with 2 variables for this model, and this one is less clear. Really, it looks like it's almost just 1 variable. So that's good. So if I had a longer list, for example, I might want to just say which.min actually I think we can just use which.min, and this is going to tell me that the second one, so this has the CP says that the second model, let me say it like this. CP says 2 variables is best. Okay, and we can do the same kind of thing for the BIC. But in this case, we have to be a little bit careful. Oops. I just want to change this to min and this one to BIC. So the issue is that, we're into the negative numbers, but we can still actually use the same information here to find the best fitting model according to BIC, which is also 2. It is the most negative in this case. So that's the interpretation. And it's okay that it is negative. Okay, it's usually, you usually get a mixture of positive and negatives. I mean, not in one. They're either usually all positive or all negative, so it's easy to interpret. So moving on, we've kind of looked at that before, but what I want to do is I want to do the selection based on the holdout method, which, we haven't gone through this piece. We've only picked based on these. So what I'm going to do is I'm going to call an object select. And select is going to be summary fit $out mat. Okay, and so what does that mean? Well, actually I could say my summary, but anyways, select. Okay, so it's just this out matrix. And I'm just going to literally go through each one of these models. So I'm going to write a for loop. It's going to go from 1 to 6, and it's literally going to pull out the predictors in all of the different models and reconstruct everything and record the error. And this is going to be important because we're going to compare it then to the bootstrap. So now that I have that matrix, I'm going to have to think about what I want to track in the loop. And I'm going to track the train error. So I'm going to make this an empty vector, and the test error. And now I'm going to go for I and 1 to 6. I'm going to go through and I'm going to pull out the model. Okay, and so in order to do that, I'm going to call this variable temp. Oops. And temp is going to say which select I throw is equal to star. Okay, so this is how I like to do things. I put that in, and then I say I is equal to 1 because it's the first iteration. And so when I'm developing the loop, I kind of do this piece by piece, and it tells me that the best first variable model, it says which is the index of that vector, select I, so the first row is equal to star. And if we look at select, we know that it is weight. Okay, so it should be the fourth item in the first row is weight. That's the one that is picked in the P is equal to 1 model. Okay, and so now what we can do is we can look at, now we had a training set before, okay, and if I look at head training, it looks like this, okay, and so the problem here is that the index temp says it's the fourth one. And if I look at 1, 2, 3, 4, I'm at horsepower because the response here is in the first column. So I have to be just a little bit careful. So I'm actually going to say temp is equal to temp plus 1 because I want to give it the right position here in this piece. Now I'm going to make two matrices called reduce training and reduce test. Okay? And I think you kind of probably get the feeling of what's going on. The reduced training is just the training set, and it's going to be subset. Now I don't have to subset the rows because I've already done that. Remember, if I look at the dimensions of this data set, it's only going to be about 80% of the data there. But the columns I want to keep the first one because that's the response, right? And I want to keep this one temp because those are the variables that were found to be important. Okay? And then when I run this, I want to run it, but I want to look to make sure it's doing what I think it's doing. Okay? And in fact, these are not the important variables because I forgot to run it all the way through. Now head, red, training. Okay, now we're okay. Right? That's exactly what we would hope to see. Now we do the same thing with the test set. And what we're going to do is we're going to look at the first column because that's the one that's the response. And then again, the same piece. The reason we want to do this is because we want to automate this. And so we can do a reduced fit. And the reduced fit is a linear model. And we can use MPG twiddle, and the data we're going to use is actually going to be the reduced training set. Okay, this is nice because now I don't, so why did we do it this way? Let's just talk for a minute and try to understand exactly what's going on. So we had a full data set. It had like 7 variables or 6 variables or whatever. And so we want to use this in the most generic form. Otherwise, if we look at select, when we get to 4, when we want to evaluate the 4 best models, we'd have to look. Okay, we have cylinders, we have horsepower, we have weight, and we have year. And you'd actually have to write all of those variables down. So this is a quick way of just subsetting the data so that you use everything in the columns. You make these little subsets, and now you never have to change this. You never have to think about it. Now for 6, it's like, okay, we could actually do it 6 times, and it wouldn't be so bad. It would take a little extra time. Yeah, but what if we had 200? You see what I'm saying? So we want to try to think a little bit smart and how we can generalize something and when we're writing these kind of codes. So here we write pred train, and that's going to be equal to predict red.fit, and the new data is just going to be red.training, just as we did before. So these next few lines are going to be like the same exact thing that we were doing before. And we'll do the same thing for the test. Okay, so we just kind of run through this piece. Uh-oh. A typo. Testing. And again, another typo. It's actually very late. It's 10 o'clock, right? Saturday, so I'm making some mistakes here. Okay, so let's see. Pred.train and pred.test. Okay, so we're kind of in good shape here. And the test error, it's going to be the same exact thing that we did before, and so why not just go up here and grab it? Okay, train error and test error, right? We called everything the same, right? We are using pred train and pred test as the variables, and so we can just do this. And of course, we have y test and y train that we did right when we started this heading underneath here. We recopied those, so that's good. Okay. And so now the only thing we have to do is we have to store this stuff. So I'm going to cheat and I'm going to look to remind myself of what I called it. I'll just copy and paste this and bring it down. Okay. All right. All right. So we have the training error. And what we're going to do is we're going to so we start with the empty loop, then we build. So we want to tack everything on top of what we already have, and we're going to add to it train error at each iteration. And the same is going to be true for test error. We start with an empty vector. We simply want to bring that vector along with us at every iteration, and then we're just going to tack onto it this test error. Okay? And that's it. Let's run this thing and see what happens. And I'm going to run it right from the top here, from the set seed piece. Okay, this is promising. No red arrows. So this is what we have for the training error, and this is what we have for the test error. Okay, based on what we have done. So, maybe we want to kind of plot the results. So what I'm going to do here Now we could of course figure out which is the minimum and whatnot, but we kind of want to see the behavior because remember, we're thinking about this one standard error rule. Even though we don't have standard errors, we kind of want to see how closely these things track, and we see that they track pretty closely. Um, but also, we want to compare to the bootstrap, and so we're going to plot it anyways. So what I want to do here is I want to create some generic axes, and so here sometimes what I do is I look at the two things I'm going to plot and try to figure out where the y should be. And so here we'll take the maximum of the two, test error store, and the lower is the minimum of the same stuff. So I'll just copy and paste this. So I do this a lot because in practice, the way R works in terms of graphics is in layers. So if I decide I want to plot this one first, then it's going to go by this axis. It's going to try to determine the optimal axis based on the training error, whereas I'm going to bring the test error in, and that might be in a totally different space. So it's just kind of a pain. So my upper and lower are going to serve as graphical parameters, okay, for the bounds on the error piece. The x-axis is the same, but we want kind of a graph that goes between these two. We want to have a little leeway there. Like I'll probably start at about 10 and end at like 21, but that's the rough estimate of where this thing sits in space. Now I use quartz, but you should use X11, and I'll plot train error store. And the type of plot I'm going to do is going to have O's. LTY is 2, and I'm going to color this in blue. And my Y limit is the one that I've been kind of fussing with here. Y limit is equal to C. I have to give it an upper and a lower, so I'm going to use lower minus 1 and upper plus 1. So it gives a little bit of leeway. And for my X label, oopsies, I'm going to have K as the label, and the Y label is just going to be error, and the main heading is going to say model selection. Okay. All right, so once I have plotted my training error, I actually need to plot the test error too. And to do that, to plot on top of that, I have to use a command called lines. And it works the same way. I'm going to give it the same information almost. I don't need to tell it everything because all of the labels and stuff are fed into from the first one, and they will stay there. Okay, so let's plot this and see what happens. There, this looks really nice. This is what you would expect to see. And so we have, I've put down dots and a line so that we can see, first of all, the trend between the dots, which isn't always easy to see if we don't have the line there. And we can see the training and the test error here. And I'm going to go even further, and I'm going to put a legend in. Legends are kind of a headache to do. I don't normally put them in because they're so bothersome. But here in this case, I know we can do it. LTY. Okay, color is going to be blue and red. So legends are a real headache, and R should really be smarter and know exactly what you've plotted and how to put it in. MATLAB does it very nicely. Really drops the ball in this regard. But here we can have this information up top. Okay. Okay, so in this final part of the lab, we're going to actually look at calculating the error in a different way. In particular, we will think about calculating the bootstrap test error for those models up here that we found to be the best. So I'll say bootstrap prediction error, and this is going to be for the best models of size k. Okay, so that's good. Now there are a couple of functions that I want to make you aware of. One is called boot. The other one is called bootpred. Boot is actually a more generic function, and we'll talk about some of the things that we can do with the bootstrap. We know already that we can basically use any type of statistic here, and so this is a very general one to find a particular statistic based on bootstrap resampling. But the bootstrap prediction function is specific toward finding the test error. And here you can see some of these terms should look familiar. The 0.632 estimate is the one that we're going to be looking at. Optimism, apparent error, and all we need to do is give it x and y, the number of bootstrap replications that we want. That's the number of resampled data sets. But this function is a little bit unique because it has three things that require functions instead of, the usual either options that we give or the data itself. Here we have to actually feed it a function. So I want to walk you through how to do that. And actually, we're just going to copy what they do here because they do it exactly for the least squares fit. But they use a function called lsfit instead of lm, and that's just because it's easier to work with this x and y. It's not a formula type setting, and so we're going to just actually steal these functions and we'll walk through them. But you could have, in theory, any fit you want to have, least squares, discriminant analysis, anything you want to do with the function. That kind of speaks to the method or the classification. The prediction is the actual prediction. In this case, we look at actually multiplying the matrix X, and here we augment a column of ones for the intercept by the coefficient, so we'll do that as well. We could also use the predict function, although I'm not sure that it works in the same way as we've seen it before with lsfit, so we're just going to steal these for now. The square error, this is any loss function, so you can think that these three things can be modified, and you can actually apply the bootstrap to any technique. So what we're going to do is we're going to create functions that feed into the so-called bootpred, and beta fit is going to be a function. Now, I'm not sure if we wrote functions yet in this class or not. So when you write a function, it's real simple. You just have to tell it it's going to be a function, and you tell it what the input is going to be. In this case, it's going to be x and y, and we kind of do these little curly brackets, and everything that's in the function sits in between these brackets, and that's it. ls fit xy. Whoops. Okay, so that's going to be the fitting for the betas. It's the one that gives us the estimate, and if we want to predict, so actually if you do help ls fit, you can see that this works like lm. It's just a least squares fit, and here they tell you something. LM is usually preferable, but I think we're going to use this just because we don't want to. It's easier. It's already in the example, so we'll just take advantage of it. And anyways, it gives a good practice in dealing with another function. So we use the fit the input to this beta predict, if we want to make a prediction, is we'll input the fit, and we will input x, the data x, and actually if we just pick that up one other time, we can see that the value of this function is going to be, let's see here, cof. Okay, this is going to give us the coefficients for the model. So we can use that, and we can actually C-bind ones to our data set X. And this means a multiplication, a matrix vector multiplication. If I do this weird symbol, it's a little awkward. But we can do fit, and we can grab the coefficients. So this is, again, just from the example in the help file. We'll use the same. And we'll use function y and y hat. And, okay, here we're going to have the residual sum of squares, y hat, quantity squared. Okay, so the first thing we need to do is run all of these. Okay, and nothing comes out. It just reads it into memory, and it knows now that that is in fact a function. And now we know kind of that we have written these functions that handle x and y, so now let's just kind of revamp our data set to fit into this framework. So I'm going to make an x, which is our auto data set, and it's going to be columns 2 through 7, as it was before. Okay, and now we need our y, and y is just auto, and it was the first column, this MPG or whatever. So here we just simply create x and y, and let's just practice here what we're going to do. So sometimes before I automate something in a loop, I like to kind of look at one case. So practice, so without loss of generality, let's look at a single model. Okay, and so for this, we're going to kind of play the same game we did before, and let's just take a model. Now we know we're dealing with the same information. We have this guy, which is, summary, is our select function, and we also have kind of this one, which tells us which one has the star. Now we don't have to add 1 to it this time because we're not dealing with the data set. We just have this data which is parsed directly into the columns of the predictors and does not include the response variable. So that's one nice thing. So what I'm going to do is I'm just going to repeat these two commands down here. And instead of using I, let's just try, for example, the third model. Okay, and so the third model, if I look at temp, I can see that these are the 3 important variables. Okay, and so now if I can, I'm going to call this res1, results 1, and this is going to be bootpred. I'm going to use the function bootpred. Now I'm going to use x, the data which I created here, except now if I do head x, I can see that this is what the data looks like, and if I do head x, and I only include the columns which I'm going to pick up through this, temp variable, the important ones, then I want to just make sure that they match what they're supposed to be. So it should be cylinders, weight, and year, cylinders, weight, and year. So this is good. So we have the data in the form that we want. And if I look at y, okay, y is, let's just do y 1 through 5. Okay, it doesn't give me the variable name, but I know that that's MPG. So here we can just build it right into the function then, and we can say we want all of the rows, and we want the columns that correspond to this, selection of the most important models for a 3-variable model. So this is the 3-variable models. I'll say that's the best 3-variable model. Okay, so here we look at that data, and now we want to include the response, and we want to tell it the if I look at bootpred, we want to tell it the number of bootstrap samples. So I'm going to say nboot is equal to 50, which is kind of small, but it's fine. Now I want to include, I have to include my three functions just like this: theta fit, theta predict, and error.measure. And let me see here, theta fit, theta predict. Make sure I call these things the right thing. Oh, geez, they call it theta, and I'm calling it beta, but it doesn't matter because as long as I put them in the right spot, it should be fine. So here we're going to say beta fit and beta predict and squared error. Okay, so those all sit in the right one. So actually you could do it like this: theta.fit is equal to beta fit, theta.predict is equal to beta predict, and finally error.measure is equal to squared error. Now you don't have to put those things are equal because it's actually sitting in the placeholder. You know, if I count as 1, 2, 3, 4 over, 1, 2, 3, 4 over, so it knows exactly, you know, what it is, but it doesn't hurt. So now let's just go ahead and run this piece, and I'm going to keep this in the background because we're going to have to go back to it in a minute. Oops. Let's see here. Oh, there's a mistake here. There should be a dot. And so it ran. It was very quick, so it's resampled 50 different data sets, and it fit them all, and it just took less than a second here. So if I do summary res 1, I don't get much information. If I do names res 1, I also get something weird, and I don't know why it comes up like this, but it did the same thing last year, so apparently hasn't been really kept up very well, but it's kind of lazy. So if you look down here to the values, this information sits in these fields, but they're not labeled. So the last one here, the last one is the call. This one here, if we do the matching here, is the apparent error. Sorry, the first one here is the apparent error. This is the mean value when it's applied to X and used to predict Y. The optimism gives kind of an estimate of the difference between the training and the prediction error. And finally, the bootstrap 0.632 estimate of the prediction error, which is the one that we're interested in. So another useful estimate is this apparent error plus optimism, which will end up to be close to this error 0.632. And let's see here. So that's just and so this is the optimism, you can see is small. This is the apparent error, and let's see, if we do res 1 plus res 1, 2, okay, these are pretty close to each other anyways, okay. So this is going to give us another estimate of our error. And we didn't have to do too much here. We just have to put in the bootstrap replications. Now, of course, that was pretty quick. And if I do 500, let's see if there's much difference. It takes a little bit longer. But if I look at res 1 now, they're just about the same. Nothing has changed very much. So now, so this was just an example of practice of a single model. Now we want to go to task here and actually generalize it and search over the best possible subsets of size k. Okay, and so let's do that. And all right. We need to implement the same thing that we did before, but we're going to want to do it in a loop. And so the loop is going to have a very similar structure from the one that we did. And we're going to create a vector here called error store. And it's going to be the empty vector. And now for I in 1 to 6, because there's, let's see, were there 6 possibilities before? Let's do dim x. Oops, dim x. There's 6. There's 6 possible variables. So we're going to find the model, the best 1 variable model, the best 2 variable model, 3, 4, 5, and 6. And so to do that, we're going to actually start by pulling out the model. And there we're going to use the same thing we did before. Temp is going to be to find which select, and the ith row is equal to this star, right? Because remember what select looks like. Okay, it's going to go through each row and do that. And then I'm going to call the fit res, and I'll use bootpred x. Actually, you know what I can do? Is I can just copy this. That's the exact same command that we're going to use. And so instead of res1, I'm just going to call it res. Doesn't matter. And I'm not going to do 500. I'm just going to do 50 to show you. You would usually run as many as you can. This is such a small problem, it's pretty easy. But the error store is going to be the storage vector as it was before in the last iteration with this res, the third field, which is the 0.632 estimate. Okay, remember if I look at res 1, the third one, this is the one we're interested in here. We're just going to tack that on at the end. And so if we run this, it ran pretty quickly, and we can look at error store, and this is the error that we have for this problem. But now let's go ahead and look. What I'm going to do here is I'm just going to scroll up here, and I'm going to copy and paste this. This was the graph that we generated before, and so let's kind of plot these now and see where they sit with respect to what we found. So what I'm going to do is I'm going to copy and paste this down here, and I'm going to add another line to the plot, and that line, so I'll do lines. It's going to contain this error store from the bootstrap, and the type is going to be this O. And I'm going to create a different line type. This is all in the par settings for this one. And I'm going to color it green. And so once we have that, we just have to change the legend and add one more thing to it. And we have our training and our test, and we also have our bootstrap 0.632, which is green. Now, I always have bad luck with plotting, so let's see if this actually works. Okay, and here it is. This is kind of nice because it's just as we would expect. We have our training error is low, our test error is up here. This is based on the subset selection piece, and the bootstrap prediction error is somewhere in between these two. Okay. So it is a nice method. We didn't have to think about, if we got any unfortunate splits or anything. The only thing we had to think about is if we're running enough samples, enough bootstrap iterations, and we can see in situations where we have a lot of predictors, so if P is very large, if the number of columns in our X matrix is very large, then we have to be very cautious about how many samples we run, make sure we approach some kind of convergence. But in a small setting, it's very simple to do. And so this is a nice way of doing that. Now, I will do a little bit of background and see if there is a way to estimate the 0.632 plus estimate. That's the one where we directly estimate a overfitting parameter. And that's particularly interesting for situations where we have high dimensional data and we tend to overfit. And we can also have problems when we have class imbalance. So we have to be a little bit cautious. This, however, is a good estimate. I use this in practice quite a bit. Um, I will look into the 0.632 plus estimate. As of last year, either the function was there and it wasn't well done, or it wasn't there at all. So I will check into that. But for now, just to recap, in this piece, we just simply looked at, again, the usual thing that we do, the holdout method. Then we look at kind of looking at how that performs over different subsets. We also looked at the BIC and CP statistic, and finally we did the bootstrap, and we kind of see what we saw that we would see in class, that it sits somewhere between the training and the test error. And so if I were to use this plot to pick a model, I would certainly pick, this is an easy one, I would definitely pick a two-variable model. Even if these did kind of stay the same or go down a little bit, they're not changing too much. This is where we see the big drop. And if I were interpreting this, I would say that I would talk a little bit about this and say the best two-variable model includes, includes weight and year. These are the two most important predictors of the different variables, or of the response, which is MPG. So that should give you an idea for how to work with this.